I'm Francisco, but please call me Paco. I work for Five. I've been at Five for 3 years now. And what I wanted to tell you about today is the kind of problems that we've solved and the kind of problems we are solving now, and why it is a super interesting job that we get to do every day. But all the cool stuff that we do, that would only happen that only happens because I'm lucky to turn up every day to the office, virtual now. This is my living room, but to the office with an amazing team. So I wanted to introduce the kind of the team we have. So our team is distributed. We go well for the last year. We've all been working from home. We were very early working from home because that was in the safest way, and we adapted very quickly. And we are 135 people roughly. We've got people with PhDs, we've got people with a master's degree, first degree, we've got some vocational training people. We speak at least 32 languages in the office, and we've essentially we've got like 6 offices all across the UK. This team is I'm very lucky because everyone is really good, and there's a lot of collaboration in between teams and offices, and we always strive to do that and to do a bit more of that. And this is more or less what it used to look like at the top, because that's from like some time ago, last time we met all together. And these days we get a lot of video calls. We go on Gather Town, and that's how we try and keep the team together and the communications flowing. The way in which we work as a team is sort of more or less we try and adhere to these principles. So as I said, we've got quite a few big questions that we're trying to solve, and we're trying to find the best solution. So we know that we don't know everything, so we're constantly learning. We're always trying to understand it better and to see if there's a different point of view we can take and a better solution that we can bring into. With that, it comes with the fact that we are doing, as Paco has said, we're doing cutting edge science for some things, and once you get some cutting edge science, you need to, in order to bring that into a product, you need to put it into you need to take your prototype and make it into a well-engineered product. So this is one of the things that we also aim to do, and we spend a lot of effort trying to do that. And sort of the third principle is that we aim and we try and empower everyone in the company to have impact every day. Impact can have many different ways. Sometimes you just fix a very urgent bug, others you'll just help someone who's not having a good day or who's stuck with a problem that happens, and we try and help each other all the time. And at the same time, we also try and remember that, especially over the last year, that we've been behind the screen, and it's only like a name. It's like there's a person. So we try and work as a good team, like rather than there's a bunch of individual contributors. So we try and aim to just we only win if everyone wins, if that makes any sense. So this is the kind of approach that we have as a team and how we try and make things. And I would say it works well because we've got an excellent team in the company, and that's why I get to show you all the cool stuff that I'm going to show you right now. So first, I would like to start with a little bit of history. So Five has been going for 5 years, and the sort of headline is that we were the first ones to bring self-driving cars to London. We did that as part of we developed a level 4 prototype, and we took it on the public road in London as part of a project called Streetwise. We took also members of the public, and we did about 1,300 miles of passenger trips in London. And these are some images from that trial. As you can see, we have a safety driver on the car, and the reason why he's got his hand around the wheel is because he's ready to grab the wheel at any point if some risky situation arises, or if the situation goes outside of what the software is spec for. Because remember, level 4 has a defined set of circumstances under which you can operate it, so it's not a full autonomy, which would be the level 5. The way we developed this, so I'm gonna play this again. So we took it on We did it on a lot of miles on the road. We have a circuit. First, we would take it on a closed road circuit. We would do quite a few tests and a lot of testing there. Then once we were sure that that release of the software didn't have any regressions or any bug, we would take it into public roads. That was a lengthy process. As part of the development process, I can recall one day where I spent about 7 hours on the car, and I was just trying this. This was not safety critical, but my aim was to try and smooth the braking, and that involved just standing on the top of a small slope, driving for like a meter or two at 1 meter per second, and then braking, and then reversing, and then doing it again until it was completely smooth. And it was very fun for the first 3 hours. The next 5 were a little bit more boring, I have to say. But the initial development we did, and if you're familiar with the space, you would have seen all the press release over the last few years of all the players saying, "Oh, we've done 1,000 miles on the road, we've done 10,000 miles on public roads." And one of the problems that this has is that it requires a lot of time and a lot of effort. And over the last year, most people possibly have not spent a lot of time on a car, but if you have, hopefully you've been lucky to realize that most of the time on a car is quite boring. This is a straight line. There's nothing happens. And when you're testing a system, what you would like to go is you want to go to close to the failure modes or to the error modes, and you want to find where the bugs are. So that's what you're going for. So part of what we realize is, and you might be thinking this now at the moment, is like, oh wait, so you were just essentially doing everything in the physical world. So why didn't you think of, like, creating a realistic physical model of the vehicle dynamics and then have a good simulator that would actually simulate all the different agents, and then come up with a way of describing what a driving scene is and how you actually put all the different agents on a scene, and how you can recreate what would be a dangerous situation, all in simulation that would be safe. And then once you have that, why don't you run, say, 1,000 or 10,000 simulations? And now that you're doing it, you might as well just automatically analyze all those results and pick up the most important ones, so your engineers can actually spend quality time looking at the most important problems. And that is precisely what we've been doing over the last 2 years. That's we started 2019, and we've been building this software, this sort of tool chain that is that is trying to answer this question, which I know is not a properly formulated question, because it's a full system. It's not, so a unit test doesn't apply, but it's quite catchy. So that's why I wanted to place it this way. So what we've been doing is trying to develop the tools to be able to continue doing and improve on what we did with the level 4 prototype, but to do it better, faster, cheaper, and more importantly, safer. And in order to do that, so one of those questions that I've mentioned that we have to start answering, and we had to come up with good solutions, is how do you describe it? First thing is you need to place your simulation somewhere, and that somewhere needs a map. So unfortunately, for a self-driving car or an ADAS system, to do realistic simulation, your Google map or Citymapper map doesn't cut it. You need a slightly more accurate, or quite a more accurate map. And luckily for that, there's an existing standard format. It's called OpenDrive. It is it's quite common in the industry. It has certain caveats. So it's a huge file. It's an XML file. It's quite low level, because if you look at the right, and hopefully that's the one time in your life you have to read an OpenDrive file, it's just a lot of geometries, and you have to define point by point. But it works. It's quite, as I say, it's quite standard. There are a few companies that can create these maps. There are editors that we can use, and that gives us the first layer that we need. You need a map to place all your simulations on. And so now that we have a map, we've solved this problem. This is a solved problem. We solved this one. What do you do with it? So you need to put your agents. You need to describe your driving scene. On top of it, you need to be able to work out what the simulation looks like. And luckily, there's another standard coming up, or there's like Open Scenario 1 and 2, and the first one came out of European and OEMs and tire suppliers. And this is what we adopted. We've done a few internal improvements and optimizations, but essentially we just use the standard. And this allows us to describe all those scenarios that we were thinking about, that you have to drive 100 to 100 miles, or I don't know the numbers off the top of my head. You have to drive a lot of miles on the public road to find something interesting. Here we can concentrate and make every meter of simulation, every second of simulation count and bring value to both our customers or our engineers that are developing the autonomous vehicle features. Because it's simulation, so you can actually create dangerous situations, and it's fine. It's all bytes and ray tracing. So what does it look like? Again, it's a very low level. It's a very descriptive. It's something that you definitely don't want to spend your days writing an XML file like that, because it would take a lot of cognitive load and it wouldn't make it. So what we've done is we created our file scenario editor. It's got a UI. It allows both development engineers, quality engineers, verification engineers to create those scenarios that are important, those scenarios where the car would actually, where you would expect to exercise all the emergency braking or things like that. So you can do that very safely, and you can do it in simulation. And more importantly, you can repeat it every time you make a change to the code. You don't have to go on the road and then drive 100,000 miles. You can drive them in simulation, and that's the sort of the value that we are adding to the tool chain. We are actually making it easier and faster for the teams to develop these features, and essentially to also make sure that there are no regressions included. So once we've got to this point, so we've got a map, we've got the scenarios that describe the driving scenes, we've got our scenario editor, and we've got a nice database in the backend with quite a few of those. How do we? What's the next thing that we would need to do? I mean, so first thing that the first thing that, well, maybe not the first thing that comes to mind, but one of the things that is important is now we want to run it. We don't want to run 10 simulations. We want to run thousands, and we want to run them quickly, because the whole idea of this is like trying and make the whole process faster, so we can find bugs faster and we can improve the development cycle and bring again more value to or make lives easier for the people developing this and make it faster. So how we've gone about it, it's essentially we've put together a lot of technologies, and we've been working on it for a while. We've got a development process that is quite stable. We've got a Kubernetes cluster running on AWS, and on top of this, we work with a microservices architecture. Most of those microservices are written in Python, and if we really need to go fast, we'll go on C++. We try and everything runs on Docker. And our development process is quite mature at this point. So we've got continuous deployment. We deploy to production quite a few times a day. It's what I would say a seamless process. Of course, everything can be improved. It's like what we have is good, but we are constantly looking to improve the process. And this is how we're achieving this hyperscale simulation. This is how, of course, we need to. There are some optimizations. There are things to improve, but we've got a system that allows us to do this kind of simulations. And once we can do the simulations, if you think of it, because most of the interesting things are going to happen in a window of, like, say, a minute. If you run, I'm not even going to go too big. So, but if you run 1,000 simulations, and if you have to ask someone to watch to go through the visualization, we've got 2D, 3D visualizations for those simulations. By the time they get to simulation 555, they've completely forgotten simulation time. And simulation time and 555 could be very similar, and they could have like an important thing. So obviously you have to analyze that automatically. And the way we go about this, so we've created quite a few systems that allows, first you have to define how good driving looks like. Once you've defined what good driving looks like, you have to define what's the limit of the system, because not every system, I've said, between level 4 and level 5, there's a big gap of features and abilities. So you have to, and then you have to make sure it's like within this setup, within the scope of this system, is that good driving, is it not? And then you have to define what the good rules of driving are. So we can run this analysis. This is like a screenshot of one of our tools, where we can see how the system sticks to to some of the rules, and we run this automatically on every simulation, and we can pick up on the interesting cases that then we sort of show to the developers for them to pay attention, and that saves this poor person having to watch 1,001 minute simulations and trying to then keep notes of which one was the interesting and which one was a little bit more boring. And so these are some of the questions that we've been looking at. Some of the questions we have partial answers to, others we are still trying to find a better solution. And thank you very much.